So I think we can probably make it with just this one more video to close the quantum k nearest neighbors algorithm, so the quantum version of the KNN. Which again, you can check out the other two parts. The KNN is just one algorithm that's used in machine learning, and the basic idea, I'm not an expert on that algorithm, but the basic idea is you've got a training set, and then when you get an input, you basically figure out what are the nearest similar elements in your set, and then you kind of classify your new input based on how those nearest neighbors are classified. So it's just pretty. I think it's pretty intuitive. So it's a rather simple algorithm at that level. And let's recap a bit what we did in the last two videos. So basically, this paper is taken from ResearchGate, and it explains a bit of all this stuff and other people that have done other quantum versions of the KNN. This is a one specific version. And basically here they outline the steps, and then what I'm trying to do is I'm trying to build a toy version of that using the IBM Q experience, and I'm keeping this. So this is where we left last time, and I'm keeping it with a small number of qubits, which it makes no sense practically. This means you wouldn't be able to use that because you can't really do a lot with 2 qubits and 2 qubits here, based on how this is describing the algorithm. But it helps me break down the algorithm at the intuition level, because I think it's easy for, at least for me, to see stuff with less bits. And so basically the preliminary steps are just and it's pretty smart, because the preliminary steps are basically just whatever you take your feature set and turn zeros into a traditional classical 0 bits into 0 qubits, qubit 0 and qubit 1. So just it's a simple mapping, and so basically this is where we start making usage of the actual quantumness. So it's like construct a training set superposition, and that was that's a super interesting thing, because we will see how they use that in the main steps of the algorithm in a second. So basically, exactly, so that's what they do, right? So you have superposition of, and in this case I'm using, just to represent the training set, I'm just using 2 qubits, which is, you can't really that's, I think that's too small for this to be anyhow practical, but it helps me illustrate how they use the quantumness later on. The main steps of the algorithm is input a testing sample, taking the same method to transform it into a quantum state. So the same idea. So basically, but it's so where you want to end up is step 2, prepare the unclassified state in the first register and the training set in the second register. So the only thing this means is so these 2 qubits is going to be, for me, the register where we keep the training set. I think that's how I originally thought about it. And then this is my input. So you kind of pack them all together, but you have to understand that they're conceptually separate. And then so now it's so now I've prepared this, right? So, and my for the training set, I just put those 2 qubits into a superposition, because I really don't, I think I really don't care really how. So for me, it's like my training set is 0001 1011. So that maybe spoils the whole thing, but it's just, let's assume that's the training set, and let's assume that, I don't know, the first qubit, the qubit 0 is sort of the category, right? Because I think that's what they saying here is the training set should be, so you've got here like this V1 and Vn, and then C. So C is the category, because the training set is already classified. In my case, what I'm doing here is just I'm having 1 instead of having n, right? So my n is 1, and then I'm having the category. So it's stupid, but I think it's going to help me understand, because I want to understand how to use the quantum, how to apply quantum computation to this, and how do they design the algorithm. And because you can easily get lost with all sort of generic mathematic formulas that try to kind of pack everything into one generic formula. And then prepare the unclassified quantum state the same. So for me, the unclassified is just 1, 0. So I'm basically taking here and saying it's a 1, and here doing nothing, it's 0. So basically, up to this point, we have prepared both inputs. So the training set is in a superposition, and then the other one is my input. So prepare blah blah blah. Good. Then record the difference between this and this in the training set. Store the result dd in the first register and reverse the value. So, and this is actually pretty smart, because what happens is, so now you got to calculate the difference between your input and each of the different elements in your training set, which in my case is the superposition, so 0 0 0 1 1 0 1 1. And so you do this by using those two control nodes. It's just that's how you make the difference in this case, which, if you pay attention, so if I let me remove these things, because then later on they tell you negate that, but we'll go to this. So that's where we left it. So basically what you have here, so now this is like the minus, right? So this is where we've calculated the difference. So pay attention that here, for example, here's like 0 0 1 1. So 0 0, right, is the difference between my input and that element of the training set. So pay attention that, because, and that's the beauty of this, is because the training set is a superposition. So this means by just applying those two gates, I am immediately encoding the difference in, across the entire superposition. So and my input is 1 0, so 1 0 minus 1 0 0 0. So that's correct. Here's 1 1 is the element of the training set. It's too small for me to mark with red, but it's 1 1. So the difference between 1 0 and 1 1, then it's this 0 1. That's also correct. And here, right, 0 0, it's the element of the training set. So 1 0 is a difference. So it's correct, right? So this is really actually the first spot in the algorithm where we're using the quantum advantages, the quantum features. So we're basically just by using 4 qubits, we are creating a superposition where we are encoding each element of the training set and what's the difference between your input and each of the elements. In a classical computer, you would have to run through all the, in my case, four elements in the training set and calculate that. And here is just bam, it happens, right? And that is pretty cool. And so what happens next is they say negate them. Why you want to negate the minus? Why you want to negate the difference? It's my English sucks sometimes. Because, and there's a lot of blah blah in here, which is needed for the paper, I guess. But I think the way that I understand that is that by negating it, then you can arrive mathematically to that conclusion that so. Because this is a trick they use for the next step, which is, okay, so now you have all the differences. So how do you calculate which ones are the closest ones? And you're close, you have to define that, right? So that's the K in the KNN. So what's you want the 3 closest, right? So in this case, they do this by playing a bit with the maths and defining a variable L, which is defined like that, but you can ignore it, and then they define like a variable like a variable A, which is L plus D. Forget about the details. The concept is they are basically going to define, so these are they are going to define they're defining here a constant A that they want to add to each of these differences that have been also negated, because once you add them, they can check if, so we can check then in the algorithm if this addition spills, and if this spills, it means that they are the ones you want to get, I think, right? Because that's why we're negating it, because then it means the Hamming distance is smaller and equal than T. So this can be determined exactly. This can be determined by whether the addition of each of the different elements plus A overflows or not. Exactly, spills, overflows. So I hope that was understandable. So the trick here is you take that difference, you negate it, and then you add this constant a, which you can make up, right? And that's what we're going to do right now. And so you then want to check whether it overflows or not, because the ones that overflow, it means that they are below the threshold where you will consider them neighbors, right? So you will consider them to be candidates for then calculating the class or the label you wanna put onto the new input. So step 6 is to define a projection operator. So I don't quite get the way this is defined in here, because basically what they say is so once the addition is done, we select the most significant qubits and use a quantum OR to get a signal cond, which indicates the condition of Hamming distance. So this is all, it's just mechanic. It's just a mechanism to figure out which elements you pick and which not. So I guess you could do it another way, but what they say is then you do all the addition and then you just pick and make an OR gate, and that tells you which ones spill and which ones overflow and which ones not. So that's kind of step 4. But in order to do that, they say, so here they introduced earlier in the paper a quantum circuit for doing A plus 1. And so they want to they reuse that. I think it's in figure 5, that's what they're saying. So, sorry, not in figure 5. Here. So here you have the addition of, that's one of your D elements, and then those are the bits that encode your A, right? So I don't know. I guess we could add 2 more qubits. I don't know if that's going to be that's going to add up to the mess. Maybe we can just add 1. The thing is, with 1 qubit, I'm thinking maybe that's not. So I'm going to add 6 qubits. So now those 2 qubits will be the A that we are now adding. So we are going to be adding. We're going to be adding this. Now it's our difference, and this now is our A. So we now want to kind of add those things. But I think I might have to add some more elements in here. Okay, so I have to add at least another one, which is then this. Which is this bit, I guess, that tells us whether it overflows or not. I think. And then we're gonna make an OR. Okay. That will. Let's first finish the step 4. But what's step 5? What's the step 4 step? What's step 5? I think that's a mistake. So I think we have to add another. We have to add another qubit. Yeah, so that's this here. And so now we're going to implement first of all, not to forget about it, these ID gates are just to keep the circuit readable. And I start to smell that soon I'll have to switch to the actual coding, so to using maybe Qiskit and then importing the OpenChasm code here, because I think the thing is I still don't feel super comfortable with a big amount of qubits. So I don't know. It will take a while probably, but I will soon switch to just copy pasting the code here and then seeing the circuit. I just like it visually. I think from an intuitive perspective, it's super helpful. So now we've got them negated. That's where that's where we finished before. And then step 6. So we're not recapping anymore. Now we're going for the actual video. So step for the actual finishing these up. So step 6. Sorry, step 4. We want to compute the Hamming distance and label the k nearest neighbors of the testing sample according to a distance threshold t. Exactly, so that's what we're saying. Okay, so now this is the adding step. So now we're going to make the adding and the OR. So the adding and the OR in this step. How does the adding look like? So I don't know if I can do that easily. It's a double control knot. It's a double control knot. I'm not so sure I understand the circuit really well, but so at the end you're supposed to end up with A plus D in here, right? So if we have, say if we have a 0, because we do this for each D, so we do this for, so for each D, and then for each D we're doing, so we have to kind of do this twice, exactly. So we're doing this twice, right? I think there's somewhere in the final circuit I saw, exactly. So you're doing this twice for each D, D1, D2. In our case, we have 2 Ds, so we're gonna just do it twice. And I'm not gonna care about that. I'm just gonna use the entire box because I'm just gonna use the entire, set of qubits here because we have just 2, so there's no point in just, we're just trying to understand that. And I think that I already, I mean, that's it really. I mean, there's no more magic to it. So the way they use the quantumness here is basically by putting the training set into an actual superposition. So which means that with just one run, you calculate all the distances, so to say, between your input and your entire training set. So that has a big impact because it means that you only need as many qubits as you might need to encode your entire training set, and that's it. So you don't have any more costs in that sense. So let's see if I can do that. And I might not get it completely right, but so this one is always a 1 first of all. So we're gonna kind of apply a next gate here, and I'm gonna apply a bunch of, let's do it this way. I'm gonna apply a bunch of IDs here and here. Let me clean that thing, and let's go back to the visualization here. State vector. Why is this not showing this anymore? It's too big already, probably. Gonna add another ID. Okay, so gonna do the same here. That's a bit tedious, but I guess that's I like to make it look nice. And so exactly. So now we're negating it. Okay, maybe just too much. Maybe I'll just use this. Okay, yeah, but these probably need to be ID. They need to be filled up anyway. So now we're at this point, and now we have to implement the addition. Okay, so that's going to be, we're going to make up A. For me, let's say A. Let's say 0, 0, right? So we don't need to put anything here. Or okay, let's put 0, 1, maybe. So these two gates, basically this and this. So this is my A, my constant A, and it's going to be 0, 1. And so now I have to, if I follow this, basically it's so there we have a Toffoli gate, and here we have, you see they're all Toffolis at the end of the day, but the controls change. Good. I'm not so sure if I can do this with the circuit composer, but I can try, because really basically here we've got a Toffoli. Unless that I think that means that this must be 0, so I might have to just I can't construct that with the circuit. I think I can't. basically. How long does this need to be? I don't understand. So as long as just because I just wanna, if I have two qubits, A0 and A1. So I guess this stops here. I guess this stops here because this is already for A2 and I don't care. So I think I just need to implement the 1, 2, 3, and 4 here. But this is a triple controlled NOT gate, which I can't implement in there. So I'm just gonna maybe just make a dummy thing, but you know that would be the idea. So let's see. Actually, I'm curious if you can do a TOEFL, say something like that. But what we're doing here is so between D and this one, and then the target is A0. So my A0. So sorry, I keep going back and forth. So my A0 is this guy. Wrong. No, it's correct. It's correct. So the control bit will be this, and the target bit will be that. Yeah, it works. Nice. I can do that. Awesome. That's cool. That's cool. Nice. So the first one is done. Correct? Correct. No. D, yeah, D, exactly. And no, A0 is this one. By the way, whoever designed this, the way you edit this, kudos, really. It's a really nice interface. So this is the first one. The second one has the D and the A0 as control, and then the target is the last qubit. So D, and so this is the target, and then this is D, and this is A0. Exactly. Super neat. So D and A0, right? D and A0. A0. Now this one is again D, the target. You probably can skip that part of the video if you want until I get it right. A1. D. So the target is I have bad memory. Now the target is A1. So the target is this one, and the control, the second control is this one. Bam. Bam. This is A1. And so, and this is now the trick here is, I don't know. I don't know if this means that it has to be a 0, you know, so it's like a negated control. I guess so. And I can't implement that. So I'm going to skip this. But it's obvious, you know, what's going on here, right? So, and then there is like a sort of a next gate, but I'm missing. So this is just for the sake of, you know, I can't have a triple control NOT here. So, but you would put that here right after this. So, and this is one box, right? I probably could use. I probably could pack that into. Maybe I'll try that. Let me try that, because maybe I can pack that into a subroutine, and that'll be actually pretty awesome. That'll be pretty awesome. But that's so. That here is one of the addition boxes, and now I have to repeat the same, right? But on qubit 3. Exactly. So let me see, what is the, so let me figure out if I copy that. Oh, nice. Bam. Cool. That's the second one. Can I just pack that into a subroutine? That would look awesome. So I'm gonna add a subroutine and I'm gonna call it so it says it's still working on, it's a functionality they're working on, but I think you can, this n go. Okay, look at this. So I think I can just say so I'll just call it add. I'll just call it add. And I think Q0, Q1, Q2. So the input is it has, sorry, the input is it has the D. Let's use the names of the paper, D. And then it has A0, A1, and it has this last thing. I'll just call it O for overflow. Okay, so it has like 1, 2, 3, 4 parameters. And now I'm gonna copy this, remove it. I'm gonna put it inside the subroutine. And this is of course D. This is D. This is D. And this is O. And this is A0. 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 And this is A1. A1. And A1. That's neat. So I like that. Maybe let's call it something like KNN add, because I think add is a reserved. It seems like it's a reserved. All right, okay, KNN. I'm so bad at naming, but so KNN, okay, and in theory now I could do. Oh, wow! Oh my god! No, it doesn't have any parameter. Remove this. Oh my god. That is so awesome. Nice. I'm sorry for the excitement. It's the first time I actually used that. So I'm pretty excited that I just figured it out. I hope that, yeah, and now I'm just gonna do this and I hope, yes. Oh yes. That's just beautiful. This is just beautiful. Perfect. Okay. I could just do it this way. This is beautiful. I don't like the name KNN. I'll call it A plus D. That's how they call it here. So A plus D. No, I can't use that. A plus D. And A plus D, A plus D, and I'm gonna remove this because it doesn't have any parameter. No, I cannot. I must input something, but it doesn't have any parameter. like this. Dude, I should maybe save now. Saved. Cool. So this is nice, and then I can probably do the same with the OR now, sort of the last step, right? The last step is basically still the OR. So we're gonna do an OR, and this OR is specified. Where can I find it? Figure 5. Okay, so it's just okay. So the OR, what it does is negates and applies the Toffoli gate. So it negates all the inputs, but I don't get why it goes to the zeros here. So overall secret in figure 6, the OR is like that. I guess if it's just an OR, I'll just implement it my own way, which is because it's just going to be between. I'm gonna just say the two last. I'm gonna use all of them. Oh no, it's only using the A's. Okay, so I'm gonna use the A's and the last qubit as well. So I'm just gonna use the last 3. So an OR would be what? Okay, so the last one is the one that matters. So an OR is kind of 1. Is 1 here if any is a 1, right? So I would say that it's basically what they're doing here probably. So they negate everything, and then it's Toffoli's. Okay. Maybe I should add more qubits again. Exactly, because so they do an OR, so they negate them, and then they basically do a Toffoli. This means that if both here are 1, this is going to be flipped to 1. Okay, if but it's just one of them is 1, that would probably fail. It's just a generic implementation. So I think I'm just gonna add a I'm just gonna add another gate, another qubit. Why is it not adding it? Maybe because of this. Maybe I just add this param, but I mean, okay, now it's added another one. I'm not using the parameter anyway, but it seems like I must add it. And now I just have to OR those things, right? So it's pretty kind of simple, I would say. If this is 1, then let's start from this one. So, and it goes to the 7. So if this is 1, then we've got it to 1. And now is where I must use a TOEFL, right? Because they must be so if it's a, because now I want these to be, so this is 1, but this is already 1, then I shouldn't do anything to it. So if I negate this one and now I add a TOEFL where the no. Dude, I think I feel stupid. I feel stupid. I could just probably Google it, but I feel like I have to figure it out. So they first negate them. Let's follow that. Let's first negate all this. Then they take the first two and they do a TOEFL negate. So this basically means this and this. And so this is out. And then they take the third one and this. One. And this is 1. So they're negating everything so that it's easy to detect. So if it's all, of course, if it's all zeros, right? If it's all zeros, then you want nothing. And as long as 1 is 1, then that's it. That's what you want to detect. So that's why they negate everything and they say, we want to see if they're all 1. So maybe it's just this way. Maybe the simplest, in my case, is actually, but because we have 3, right? So 1. Exactly. So we need to add another. I think I know why they're doing that. So, and now by virtue of doing that, so now you have another TOEFL gate. I have another TOEFL gate here, but why I can't do that? This, and then no, I want this and this. Yeah. So we want this and this. Correct. Because if this is 1, that's what we're looking for, 1, 1, 1. So if this is already 1, it means those were 1, and if this is 1, then it's done, and then we're done. So and in this case now we just negate that. Okay, so maybe I'll pack that into subroutine as well, so it ends up clean. But at least you've seen how I've built it. It's getting big. It's getting big. So we're gonna create another subroutine called the. We're gonna call it the or. And basically it has, I would say, 5 parameters, right? So I'll call input 0, input 1, input 2, output 0, output 1. And so and it's like that. So I'm going to take that and I'm going to say this is here. So So basically the X are all in, you know, it's input 0, input 1, input 2, and then this is E0, E1, output 0, and here we have E2, output 0, and output 1, and then we negate output 1, and we have it, output 1. And so we do this, and we have it. Cool. And I think that's it. What does it say here? So basically, there's still a. I'm not so sure if that's it though. Then there is step 6: define a projection operator, apply it on, and renormalize the result. We can get this with probability 1. I don't know what this renormalized amplitude. I don't offer a renormalized amplitude for each component. Change the sum of all amplitudes is 1. Yeah. Okay, so I think that's basically saying it's time to play with this baby. It's time to play with this baby. How? Because now we would have to add measurements on absolutely everything. It's gonna be fun. So we're gonna measure everything, because I cannot see this here anymore. So I'm gonna have to. And I guess what we want to see is which items are overflow. We're going to take at the topmost. So we're going to take at the qubit 8 measurement. Wow. If I might miss some detail, right? But we've learned some stuff. That I've definitely learned some stuff, which is this is already getting pretty big. But the subroutines work pretty smoothly. And it's actually really cool because you can pack that stuff. It would be good if we didn't have to use all the ID here, but I understand why. I think it makes the design of the circuit editor better, the circuit composer, sorry. So what if now we try to run that? Hopefully it's not going to break. Maybe just to explain again, just the general idea. And if you've just, you know, if you didn't listen for the past hour almost, so first, we're putting our training set here in a superposition. Then we are here encoding our input, which is 1, 0. Then in these steps here, we're doing we're doing this. We're subtracting that, and so in qubit 2 and 3, we're going to have here we're basically flipping the result of the operation at the minus. We're doing that just because of the way the algorithm is designed. It allows us to then use the overflow down here to know that if we are adding this with a constant a, and the constant a is defined by these 2 qubits. So, and this guy and this guy do the plus, so they sum the d with the a. And so if we detect there's an overflow, which is going to be a 1 appearing here, it means that entry in the test set is one of the neighbors. I think that's it. So let's see what happens. I don't know. I don't expect anything magical to happen because really it's a small scale version of what the paper says, but I think it illustrates the example that the quantumness here is we're putting the test set into superposition, and we're using the fact that by just applying one operation or 2 gates in this case, we have immediately all the results we want in the superposition encoded. So that's pretty cool. So let me run this. Oh, that looks ugly. Exactly. And we're going to run that on a simulator. Bam. Let's see what happens. Wow. Error running job. Yeah, maybe there's something off with the subroutines here. Honestly, I don't know. because I was getting some errors here with this with the parameters. Yeah. Does it tell me what failed? No, it doesn't. Error transpiling. Okay. So yeah, maybe this is because of this. Wait a second. Why there's some minuses in here? Oh no. Why? Parameter. Maybe because I messed up with these and then I added them again. Maybe I have to simply add the plus operations again here. So A plus D. If I remove them, do they get removed? Yeah. Maybe it's because of that. A plus D. So, and I think that the only thing that I needed to do is simply this. I kind of don't like that, the way this looks like, honestly. That's not how it's supposed to be. Is it? Why is it? I think that's not what I implemented, is it? That's not what I implemented. Why did it mess up with it? The first is A1, A0, but it does not update here. The target is A0. And the second one, it's D, A1, and O. D, A1, and O. Come on. And the third one is D, O, A1. D, O, A1. And I already said that I'm skipping one, so I could make a comment here, skipping one, because I can't build it. And then I do an X. Oh, why isn't it that? Let me just copy paste that. Why isn't it that then updated here? Okay, now it seems updated, and now it seems updated. Yeah, but I don't think that was the reason why this couldn't be transpiled. And the OR stays how it is, right? That's correct. Maybe I just messed up with it and then it just, Okay. Let's save and let's try it again. If it doesn't work, I'm going to stop here. But because you get the idea, right? Simulator run. Yeah. Why it doesn't appear? As pending result. Simulator run. Error running job. Oh, come on. It's a pity. Because I can't probably run that on a real device because it's too messed up. Error running job. No, it's a pity. But now it's running, no, transpiling. Transpiled. Yeah. Anyway, you get the idea, basically. even if I didn't get it 100% right, I think that's, we wanted to break down this at an intuition level, and that's exactly what we've done. I hope that you enjoyed this, and if so, put comments down below. Check out the other videos, and if you have any other or anything, any paper, any algorithm that you want me to take a look at, just let me know. Put it in the comments down below, and see you next time.